Recording is started. So welcome to Tuesday. So you guys remember yesterday I started talking about electromagnetic spectrum, a little bit about optics. We were looking at this page, navigating some of these formulas, solving some of these problems, and we got to this one here. So I want to go back and fill in some details about spectroscopy. Then we'll finish these last few problems from 16, and then we're going to move on to reflection. So it was originally pretty ambitious, wanted to cover all these topics today, but somebody's going to have to postpone until tomorrow. So we'll get started on reflection anyway. And so what is spectroscopy? Well, the last question we left off on yesterday, let's go take a look at that. Number 14 says, what is the frequency of oxygen's spectral line if its wavelength is 513 nanometers? And we went through and solved this, but what the heck are they even talking about? So pull up Paul Hewitt's book. Show you guys some spectral lines, line spectrums. So we're looking at something like this right here. Each particular element, because of its atomic structure, you shine a light on it, it's going to reflect the light back into the world. Certain wavelengths of light are going to be emitted from any particular element. You're seeing three different examples here. So here's visible light. Remember, this is just a very small part of the electromagnetic spectrum. This is just what our eyes can detect, right? All the visible colors, right? And these certain wavelengths will pop up. For this one right here, it says is hydrogen. This one says is sodium. This one says is mercury. Right? In each element could have some spectral line like that. So suppose you're an astronomer and you're looking at some distant planet. And you're wondering, I wonder what that atmosphere is made out of, right? And you see, let's say a bunch of, say you see a bunch of hydrogen and oxygen, say in a 2-to-1 ratio. You may say, oh, okay, well, that's maybe strong evidence that there's a lot of water on that planet, maybe water vapor. Hey, maybe that planet has is like Earth-like or might have life, or that'd be the way you can figure out something like that. What instrument would you use to get these line spectrum in the first place? This guy right here, a spectroscope, says light to be analyzed illuminates the thin slit at the left, where it is focused by lenses into either a diffraction grating or a prism on the rotating table in the middle, and then viewed through the eyepiece on the right. Okay, so they're talking about refraction and diffraction. So those are topics that are coming up the next few days in this class, but here we go. Right, now, the next few questions that we're about to look at involve, well, the Doppler effect, right? You guys remember a Doppler effect? There's some kind of frequency shift. So a car goes by on sidewalk, so it's like, you guys see a poster up here, shows the Doppler shift for like a sound waves. We're going to do the light wave version of this. Let's say that there's a galaxy that's moving really fast away from Earth. I'm about to give you guys a bunch of background and context into some of the problems that we're going to solve. So let's say there's a galaxy moving really fast away from us. Isn't that kind of analogous to a car moving away from you? So it's sounding its horns are like, but it's moving away. It's like, wouldn't that be like a decrease in frequency? Now, since speed is equal to wavelength times frequency, and the speed of light is just constant, it's just what it is, then if you have a decreased frequency, is that an increased or decreased wavelength? Lower frequencies mean longer wavelengths, right? Lower frequencies, longer wavelengths. Okay, and longer wavelengths, is that closer to the red part of the spectrum or closer to the violet part? Red, right? So here's more what astronomers will actually see when they look up at distant galaxies, especially about to draw, I guess, is these light spectra are actually shifted a little bit towards the red part of the spectrum. Right? They'll sort of match the fingerprints, like we've got something that looks like hydrogen, something that looks like sodium, and something that looks like mercury, except all these lines will be shifted a little bit to the left. Now, you can use that to figure out not only how fast the galaxies are moving away from us, but also how far away they are. Again, just going back and filling in some details, give you guys some context about this. I need to tell you guys about something called the cosmological principle of universal expansion. So Edwin Hubble was one of the first people to figure this out. I'm just going to draw a bunch of galaxies, right? Just around on this paper. Let's say there's a bunch of galaxies. Actually, if you go back to like over 100 years ago, it's only been about the last 100 years so that people even realized that there were different galaxies, right? That all the stars that we feel like constellations, all the stars you can see are actually part of just one galaxy, like the Milky Way. Let's say the Milky Way is like, let's say it's here approximately. I'll label this Milky Way. Okay. What Edwin Hubble realized is that all other galaxies, well, except for Andromeda Galaxy, but pretty much all other galaxies are red shifted, which means they're moving away from us. And furthermore, the further away they are from us, the more they're red shifted, or vice versa. The more they're red shifted, that means the further away they are from us. Now, why is that? Right. So let's take a look at this spectrum. Right. So we got. This could represent electromagnetic spectrum. We've got long wavelengths on the right. We've got high frequencies to the right. And there's some visible portion where you get all the colors. So red, orange, yellow, green, blue, violet. Everything to the left of red goes infrared, microwaves, radio waves. Everything to the right of violet goes ultraviolet, X-rays, gamma rays, something like that. Okay, so we could say. And then, okay, so Doppler shift. The faster things moving away from us, the more the wavelengths get drawn out, which means it gets shifted to red. That's called red shifting, right? I did mention Andromeda Galaxy is actually blue shifted. So Andromeda Galaxy is headed towards Earth, right? But it's one of the rare exceptions. All these other galaxies move away. Now, so that was some of the first evidence that the universe is expanding because all these galaxies are moving away from us. But they're moving away kind of in a funny way. This is where the cosmological principle kicks in. Okay? And one thing that cosmological principle says is that, well, you could either say that there is no center of the universe, or if you like to think of it a little bit different way, you could say that the center could be anywhere from, so you could be standing on any one of these galaxies, and from your perspective, including us, Milky Way, all other galaxies are moving away from you. Now, how's that possible? That there could be like no center, because if you think like a traditional explosion, let's say you have like a grenade, you put it on the ground, step back, watch it explode. There is a center point to that explosion, right? Well, that's not really exactly how the Big Bang works or how the universal expansion works. So one analogy I've seen is, say, okay, now you have to think kind of abstractly with this. Let's say you take 3 spatial dimensions and put them onto a 2-dimensional surface of a balloon. Okay, so here's a balloon right here. Okay, and I'll draw all the galaxies. So galaxy, 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 galaxy. Okay. Now remember, this is an analogy, so you have to think kind of abstractly. Okay. Remember, the surface of this latex balloon represents 3 spatial dimensions. Okay, so if you blow up the balloon, would it be true that all the galaxies would move away from each other? Right? They would move, right? But where would the center of the surface of the balloon be? Well, there is no center of the surface, right? So that's sort of analogous to what's going on here with this cosmological principle. And one of the consequences of this is that the further away galaxies are, the faster they're moving from us. And when you combine that with the fact that there is a hard limit moving through space, which is the speed of light, 3 times 10 meters per second, put 2 and 2 together, the consequence of that is that there will actually be an observable limit. Right? There will be a limit to how far we can see, and everything inside that limit is called the observable universe. So I'll call this observable universe. Okay? And say you're looking at comparing these 2 galaxies right here. Right? Well, the space, and once you get far enough away and you consider universal expansion, right, how the universe expands, right? Say these 2 galaxies right here, the space between these galaxies would actually be expanding faster than the speed of light. Right? So it's not that these 2 galaxies would be moving through space faster than the speed of light, like that would break laws of the universe. We'll talk about relativity here in a few minutes, a few weeks. Right? But the space between galaxies can expand faster than the speed of light. So whatever light information is leaving this galaxy, it's physically impossible for it to ever reach us. We'll never see it. Okay? You guys see this picture hanging above my door right here? This one right here. I think I told you guys that story a long time ago. I'll recap it real fast. And then for anyone watching the video, let me share my screen real fast just to show you guys a picture of this. Right, so we're looking at, sorry, I gotta flip my screen there so I know what people on the video are seeing. Okay, that right there. So that is the whole Hubble Ultra Deep Field. So the story behind this is a couple of decades back, some astronomers wanted to take the Hubble and point it to a random spot in the night sky. How big are we talking about? Well, if you take like a grain of sand and hold it up about arm's length, about that angular space in the sky. So tiny, tiny, tiny little dot. They didn't know what they were going to get. They had to open the shutter for 2 weeks to get an image. And they might have just gotten back a black rectangle, which would have been like, oh, well, that was a waste of time and use of that, that telescope. But they got this. Right? That is as far as we can see into space. That is like the edge of the observable universe. Now, are there galaxies beyond those? Almost for sure, but well, I'll never quite know because we can't access that information because of how the universe expands. Right, so let's go back to these book problems. Now that's a lot of back context to fill in what's going on here. Now these questions, the premise is going to be, let's say we're comparing these two galaxies, and you want to know how fast are they moving away from each other? Well, that's going to be Doppler shift, and depending on how much it's red shifted, you can figure out how fast they're moving away. All right, so you guys covered that? Any questions about any of that stuff? Okay. All right, let's dive into these. All right, so number 15, a hydrogen atom in a galaxy moving with a speed of 6.55 times 10 to the 6 meters per second. Okay, now pause right here. I know that speed of light is like 10 to the 8 meters per second. We're looking at 10 to the 6. So this is order of magnitude about 1% of the speed of light. Yeah, not because this galaxy is moving through space. No. Really, it should read space is expanding between us and this galaxy at this rate. Okay? Emits light with a frequency of 6.16 times 10 to the 14 hertz. Okay? What frequency of light from that hydrogen atom would be observed by an astronomer on Earth? Okay, so we're going to use Doppler shift involving frequency, which is this guy right here. Okay, so go ahead and just plug and chug. So up here. Okay. So number 15. Okay. We're going to say the observed frequency is equal to the source frequency multiplied by this ratio. Got 1, plus or minus V over C. Okay. So V would be the relative speeds of these galaxies, because space is expanding, and C is the speed of light. And they gave us all these values except for the observed frequency. So we'll just plug in. There's going to be no algebra involved. Just plug stuff in, just arithmetic. So observed frequency is equal to, the source frequency was given as 6.16 times 10 to the 14 hertz. I'm sure that corresponds to like an actual value for hydrogen, like in a lab. Okay. And I've got 1. Okay, I got to pick plus or minus. Now let's think about this. Red shifting, right? So galaxies moving away, the wavelength is expanding, getting longer. That's red shifting. So should the observed frequency be greater than or less than the source frequency? What's it got to be? Less than, right? It's got to be a lower frequency. And the only way to get there is to choose what? Plus or minus? Minus, right? That's for red shifting. Right? Because it's going to be a decrease in frequency. So we're going to go minus, the galaxy speed was given as 6.55 times 10 to the 6 meters per second. Right, and then compared to 3 times 10 to the 8 meters per second. Right? 10 to the 6 compared to 10 to the 8, that's like 1/100. But 6 compared to 3, that's like 2. So maybe about 2% of the speed of light, something like that. I'm kind of curious to know. What is this whole piece in the parentheses equal to? What's 1 minus? Now, if you put your calculator 1 go, make sure you got everything grouped correctly. Open parentheses 6.55 by 10 to the 6, close parentheses divided by open parentheses 3 times 10 to the 8, close parentheses. And so that is 0.9782. So it is about 98% of the original frequency. So that multiplied by 6.16 times 10 to the 14 hertz. Actually, let me get rid of the 10 to the 14 part. I'll just put that in myself. Times 6.16 is 6.03. So the observed frequency is 6.03. And then I'll put back in the times 10 to the 14 order of magnitude hertz. Okay, so that's what you would see. Now, a more realistic application of this would be something like backwards what we just did. You're an astronomer, you know what frequency of some spectral line of hydrogen is from the lab, that's this number. You look through your telescope, you observe this, you're like, aha, therefore I can back calculate how fast that galaxy is moving relative to us. Okay, that's more like number 17 that we're working towards. Okay, good. Number 16. A hydrogen atom from a galaxy moving, this is very similar premise, but okay, moving with the speed of 6.55 times 10 to the 16 meters per second away from Earth, and it's like with a wavelength of 4.86 times 10 to the minus 7 meters. What wavelength would be observed on Earth from that hydrogen atom? Okay. So one of the differences between this one and last one is that we're looking at wavelength instead of frequency. Okay, big deal. Right, here's wavelength formula. But you know what? I actually suspect that there might be a typo in this question. And I wonder if you guys see what I think is probably a typo. Do you guys see it? What I think is probably not supposed to be there. Take a look at this galaxy speed. 6.55 times 10 to the 16 meters per second. Huh, what's kind of fishy about that number? And if some of you guys see it, that's faster than the speed of light. The speed of light is like 10 to the 8. This is 10 to 16. Is that even possible? Well, technically, sort of. And that goes back to what I was talking about right here. Okay? So maybe like these two galaxies might actually be moving away from each other faster than the speed of light, not because they're moving through space, but because space between them is expanding. Right? So sort of. But if that's true, are we even going to receive any light information from this galaxy at all? No, it's never going to reach us. So if this is not a typo, then the answer is that you wouldn't see the light at all. Right? The answer would be no light. But I'm going to change that number so that we can actually solve a problem. I'm going to change this to 10 to the 6. Okay, so this is solvable. Right? And the Doppler shift we have dealing with wavelength, well, they gave it to us like this, but I'm actually going to rearrange it so that, well, you guys see what I'm going to do with this. So the change in wavelength, that's what delta lambda is, change in wavelength, which is the same thing as observe. This is number 16. Observe wavelength minus the source wavelength, right? Because there's some wavelength that's being emitted, and then as it crosses the universe, maybe it'll stretch out. So there's a change, like delta lambda. That's equal to, it says plus or minus speed of the galaxies compared to speed of light times the source wavelength. Okay. And what we're trying to solve for is what wavelength would be observed on Earth. We're trying to solve for that. Okay. Now I'm going to do something that I do sometimes in here, but not very often. I'm going to rearrange this in terms of variables. Right? If you guys ever want to take AP physics, what I'm about to do, I do a lot more often. So I'm going to take the source wavelength and add it over to the right side. That's going to give me lambda observed is equal to lambda source, lambda is wavelength, right? Plus or minus b over c times lambda source. Right? And then I have two terms on the right side. We'll connect by plus or minus. Right? I'm going to factor out that source wavelength. So the observed wavelength is equal to the source wavelength multiplied by, right, now if I factor it out of these two terms, I'm going to end up with 1 plus or minus v over c. Right? And the reason I did all this formula manipulation before we actually plug in numbers and solve everything, I didn't have to do this, but I wanted to do that because that makes it look a lot like the Doppler shift formula for frequency. Look at that. This looks a lot like this, doesn't it? Right? Except it's wavelength instead of frequency. But one more thing. Back when we were solving redshift with the frequency formula, you guys remember we chose minus so that would overall decrease the observed frequency would be less than source frequency for redshifting. Right? But what about for wavelength? I mean, the wavelength should actually get physically longer, shouldn't it? And would that correspond to a plus or minus? Yeah, plus. Yeah, it has to be plus. Okay. because we want the observed wavelength to be longer than the source wavelength because it's getting stretched out over the universe. Okay, okay, and the only way to get there is plus. Okay, so that's maybe a difference from the other formula too. Okay, well, let's go ahead and plug stuff in. So we're trying to figure out what is the observed wavelength. Okay. They told us the source wavelength should have been, I'm gonna rewrite this number. They said 4.86 times 10 to the minus 7 meters. That's the same thing as 486 nanometers. So that's what I'm gonna write. Source wavelength is gonna be 486 nanometers. Okay. Is that just a prettier way to write that? Multiplied by C1, we decided to take plus because wavelength is stretching out. And here's where I'm gonna alter the V. I'm gonna say 6.55 times 10 to the power of 6 meters per second instead of 16, compared to 3.0 times 10 to the 8 meters per second. Great. That's it. You know what? I want to do a quick side quest before we just plug and chug and get the answer, which you could very easily do. Okay. Let's do a side quest here. What if something was moving at the speed of light, right? You guys get that? What if V is equal to C, right? So it would be, maybe that would put us like just at the observable limit, something like that. Wouldn't this ratio be equal to 1? You get 1 plus 1 is 2. Everything in this parentheses would be factor 2. Huh. So what I'm thinking, and I haven't really Google checked this, but just logic based on this formula, the way I'm reading this anyway, is that you can get up to twice the wavelength. Well, once you stretch out the wavelength to twice its wavelength, you'd be like at the observable limit. Maybe that'd be one way to figure that out. Okay, let's do the plug and chug part. All right, so 486 times 1 plus, go with these guys in parentheses, 6.55 by 10 to the 6 closed, divide by open, 3 times 10 to the 8. That is, yeah, that's about right. The observed wavelength is 496.6 nanometers. Right. You guys good? And 17. So this is going to close our chapter 16 problems. Okay. All right, now question 17 is actually my favorite of these questions because it's close to what an astronomer would actually do. If you guys ever become an astronomer. Looking at the spectrum of a galaxy finds that an oxygen spectral line, oh yeah, you guys remember those spectral lines from Paul Hewitt book, is 525 nanometers, but the lab value of that same oxygen spectral line should have been 513. Huh, but it's stretched out a little bit, isn't it? So the 2 questions here. Calculate how fast the galaxy is moving relative to Earth. Say like, because space is expanding between us. Okay. And then also explain whether the galaxy is moving toward or away from Earth. Let's answer that second part first. Okay. So the wavelength should have been 513 nanometers, but it's been stretched out to 525. First of all, is that red shifting or blue shifting if you're stretching out the wavelength? That's red shifting. Red shifting, is that moving towards us or away from us? Away from us. Almost everything is redshift. All the other galaxies relative to Earth. Okay, so it is moving away from us, right? So I'll leave that to you guys. Let's solve the number of parts with you guys. Let's paper. Okay, so 17. First, back up here. Zoom out. Okay. All right. So actually, I'm gonna play off this modified version of this wavelength formula that I got before. Remember, this is the textbook version of it. Then I did a couple of steps. I'm going to just pick up right from here. So the observed wavelength is equal to source wavelength times this ratio. So lambda observed is equal to lambda source multiplied by 1, I got plus or minus V over C. Okay. But we already went through the plus or minus. We said, well, it's got to be plus for the red shifting. Okay, so this is red shifting, which is the only way to get the observed wavelength is longer than the source wavelength. And those numbers were 525 nanometers for this guy and 513 nanometers for that guy. Okay. Right, and now we can calculate how fast that galaxy is moving away. There's the speed of light right here. Now, this one's going to take some algebra. Right, so now let's step through this algebra process. First thing I'm going to do is divide down the 513 nanometers. So what is 525 nanometers divided by 513 nanometers? Okay. Some ratio looks a little bit bigger than 1. That's equal to 1 plus something. Yeah, that's a little bit bigger than 1, isn't it? Solve for this v. 3.0 times 10 to the 8 meters per second. Like that. Okay, I'm going to subtract 1. And after that, cross multiply at the speed of light. Right? You guys get that? Okay. So v is equal to, let's solve this down. It's going to be 525 compared to 513 nanometers, but that cancels out anyway. Subtract 1, right, like a tiny decimal, and multiply that by the speed of light. Okay, oh yeah, a tiny decimal times the speed of light. Seems like it would make sense. Right? Some small fraction of the speed of light. What is 525 over 513? Okay, so 1.02, subtract 1, gives you 0.02, 2% speed of light, multiply by 3 times 10 to the 8. I'm looking at v equals 7 million meters per second. Okay. Now, okay, actually I wrote way too many digits. Like the 544 is not even significant. So let's do scientific notation. Let's say we have 3 sig figs to work with. I'll call that 7.02 times 10 to the 6 meters per second. That's a more scientific way to write that number. 7 million meters per second. Guys got that? All right. So okay. That's a wrap on chapter 16. All right, now move on to chapter 17, which is reflection and mirrors. Let's introduce this with Paul Hewitt. Okay, Paul Hewitt time. Yeah, Paul Hewitt.
Consider a candle. All optics books consider candles for objects, okay? Now we're going to look at the image that this candle gives in a mirror. Let's suppose right here, we have a mirror surface. Now what happens is light, let's just take from this point. Light goes in all directions. Some comes straight ahead, some comes up like this, some comes like this. The light hits the mirror in all directions. And when it hits the mirror, it boom, reflects, yeah? And it reflects how? There's a normal, a normal, a normal, a normal. It reflects such that this angle, for example, here, will be equal to this angle here and reflect like that.
Right, he just told you guys what's probably the simplest physics formula you're ever going to get. That the angle of reflection equals the angle of incidence. Now look what he's measuring the angle with respect to. See how his plane mirror is vertical and he drew these horizontal dash lines. Wait, those horizontal dash lines are perpendicular to the surface. They're called normal lines. Normal is perpendicular, okay? So normally, he's measuring those angles with respect to those normal lines, those dashed normal lines. Later this week, we'll do refraction. It's going to be the same story. Whatever angles that these things are like bouncing around and bending, we're going to measure with respect to normal lines compared to the surface. And all the law of reflection says is that the angle of reflection equals this angle of incidence. Just eyeballing it, that looks about 30 degrees. So if that's 30 degrees, that's 30 degrees. All right, next.
And up here, this will reflect right back to where it came in, because it hits flush, huh? Right in. Huh? Up here, like that. And up here, like that. And down here, like that. Where this and this are the same. I don't have that drawn very well, yeah? Like that. You get the idea? Now, you have your eye out here and you're looking. These rays here are all diverging. They're spreading out, see? They're spreading out this way, just as if they were this way, see? It's like this continue, huh? But that spread out looks to you like that ray came from back here, that ray came from back here, that ray came from back here, that ray came from back here. It looks to you out here like there's a flame here and also a flame back here. And I could draw the same rays for the bottom of the candle. That's done in your book a little bit, yeah? Okay. And the bottom of the candle, it would look to you like it's over there. And so you would see the candle here, and you would see the image of the candle. And let me ask you a question. What's the distance here, and the distance here? Begin with SS.
Same, gang. Same. All right, so this is something you guys probably see every day, right? You're brushing your teeth, you look in that flat plane bathroom mirror, and you see a reflection of yourself. The image, that's what this is on, right? The reflection is called the image, it's a physics term. Okay? Should look like the same size, like the same height, and also equidistant from the plane, just on the opposite side. Okay, so that all checks out, makes sense, right? All right. What if we bring in like curved mirrors, maybe like funhouse mirrors, like parabolic mirrors, so I've got this demo in class. I'll flash this in front of the screen too, but you don't get a good look at it. Yes, hopefully you've seen this some point in the year, walk by this. So that pig is not really there, right? Now that pig is called a real image meaning it looks like it's hovering in front of the mirror. Now Paul Hewitt's candle was behind the mirror surface, that was called virtual, but this one's called real image. There's the actual plastic pig right there. It's actually down there. So, and this is a really good illusion too, right? So if you haven't seen it yet, then I got this flying saucer looking deal right here. Walk by this, it really looks like it's hovering just above that surface. What's going on there? How are we gonna be able to create, say, a real image? Right? What's going on with those curved surfaces? So I guess at a basic level, it just follows the law of reflection. For the camera, well, it's going to show up, but here's the actual. Oh, got to take a couple of the top pics there. Right, that's over the top, and try to see. Okay. Yeah, so on the video it looks pretty good, and then you guys in class, they don't slide around. Okay, kind of see it. Right. Yeah, you can kind of see it popping up there, right? In class. So look at this here. It said walk by that. It's really good looking illusion, real image. Right, so how are we gonna get that? Well, let's look at some parabolic mirrors. Okay. Which I do recommend that you guys, here, if you don't have any paper, I'm gonna leave a stack of paper here, stack of paper here, stack of paper here. So you guys can follow along with me, unless you just want to do this in your notes, that's okay too. Okay, so we're going to do different kinds of mirrors, and then we'll eventually do refraction. We'll do some of those. I'm going to draw some ray diagrams with you guys. I'm glad you guys do some ray diagrams. Now let's start with some convex parabolic mirrors. Convex parabolic mirrors. In class today, we'll start on the concave, and then later this week we'll do refraction, and there will be a different ray diagram type setup. Okay. On this side of the page, I'm going to do 3 convex parabolic mirrors. So start with I'm going to do 3 horizontal lines. I'm dashing mine. I guess you don't have to dash yours, but this is going to represent the like the floor, things like that. Like the sort of analogous to Paul Hewitt's base of his candle. Okay. Maybe it's like sitting on the floor, sort of deal. Okay. So we're doing 3 separate examples. Okay. So draw a mirrored surface that's has a kind of a curve to it. Sort of a curve, okay. And we'll have a guy stand in like right here. Okay. This guy I'm going to call the object. What colors did I want to do? Yeah, just light blue. Call this guy the object. Okay. There's usually 1 of 3 pictures to use as an object. Paul Hewitt used a candle. I like stick figures. Another, like a third one I've seen that's really popular in textbooks is to use an upward arrow. I don't like the arrow because I'm about to draw a bunch of light rays that also kind of look like arrows, so that could get kind of confusing. But we're using a stick figure for my notes. Okay. Now, you guys know if this was a flat plane mirror, the reflection of the sky, this image would be same size, opposite side, equidistant, just opposite side. Right? Paul Hewitt just did that with a candle. But now I have sort of like a funhouse mirror. So what's the physics of this? How's this going to work? What's this reflection going to look like? And I'll tell you guys what too, you guys can try this at home later today. So whatever the result is, just look at the backside of a spoon. Isn't this like this guy's looking at the backside of a spoon? It's the same, right? So you'll see the same thing. Right. No, what's the setup here? Now this is a parabola. You guys know what a parabola is. It's like y equals x squared. So take that, turn it sideways, and flatten it. It's that shape with overlay. Do you guys think I could fit like a circle in here? Fit like a circle that could be flush to this point? Maybe you could blow up that circle bigger, bigger, bigger. But at some point, the circle is going to get too big and it's going to detach, right? So I wonder what the biggest circle is I could fit that would still fit flush to that point. Let me sort of draw what that circle would look like. Okay? Maybe look something kind of like this, just real light dash on this. Okay? So I don't want to interfere with my other pictures too much, but big old circle, right? Now, remember, this curved surface itself is not part of a circle. It's part of a parabola. Okay? But I'm fitting the circle sort of like flush up to it, the biggest circle, okay? In this circle has a center, probably right about here. So that this distance, I'm going to call r, and that would represent the radius of that circle, right? Okay, then I'm going to take half that distance from the surface. I'll show you guys why half in a moment. It'll make sense. Right? So just go with it for now. Right? And I'm going to call this the focal length. Call this f. Right? And what I just told you about the relationship is between those two. So the focal length is always half of the radius of that circle. Okay. Now, what's special about that focal distance? Actually, this point right here, I'm also going to label f. Maybe that's a little bit confusing, but I'll call it the focal point. So this f refers to focal point. Okay. And from now on, just for the rest of my pictures, all I'm going to care about is that focal point. But you guys know in the back of your minds that that's half of the radial size of a circle that can fit flush to the earth. Okay. Right. Now, why do I care so much about this focal point? Well, let's start to draw some light rays, and then you'll see why. Okay, so I'm going to switch over to pinky, maybe like a pink laser. That's what I got, pink laser. And I'm going to have one ray of light, say one laser light, going from the top of his head parallel to the ground. See how I just drew a line that's parallel to that dash 4? Right, parallel. Okay. Now, if this were a flat plane, you guys know it would just bounce straight flat. But the fact that it's curved isn't going to, boing, kind of bounce up to the left. You guys think kind of up to the left? Okay. But how much up to the left? Well, that probably depends how much it's curved. Hey, maybe that has something to do with, say, these points, like this R or this F. Okay. So let's incorporate this, the center of the circle. Okay. You guys remember he was comparing, he was measuring angles relative to some normal line, right, perpendicular to the surface. Well, if you line up this point right here with the center of the circle, that's how you can create a normal line that you can actually measure angles with respect to. Hey, this would be the angle of incidence, wouldn't it? We'll call it theta I, angle of incidence. Okay. Now that's going to bounce off an angle of reflection that's equal to that, just on opposite side of that dashed line. Okay. That's where the focal point's going to come in. And then for the rest of these pictures, I'm just going to cut straight to the stuff I'm doing right now. I'm going to pick up from this point, align it with that focal point, and that is the way it's going to reflect. Okay. So I've got this angle of reflection. Okay, call it theta R. So interfering with my title, but I guess you think okay. This theta R is equal to this theta I. Maybe they're both like 25 degrees, for example. Is that? It's going to boing. Now, how are we going to somehow though figure out where his reflection is going to be? Because his reflection is going to appear to be on the opposite side. It's going to be a virtual image, just like playing mirror, you're brushing your teeth, quick you're on opposite side. So now keep in mind that there's no light that actually ever crosses this mirrored surface. It's just bouncing off to the left, just like I did. But we're going to extrapolate backwards, just like Paul Hewitt did with the candle. So let's go back to the last one I just drew. Let's extrapolate back through that focal point. Right? It's this light ray. It's as if it was coming from behind the mirror, right? Even though it's not really, but it looks like it. Okay, so that's we're following one ray of light because boing, and then extrapolating backwards. Okay. Now let's go back to the top of his head because there's like I could draw a million different light rays, but you only need a small handful of light rays to figure out where his image is going to be, and we're about to figure it out. So go from the top of his head through that focal point. Zip. Guys, just draw that top of his head through the focal point. Okay. Of course, you guys know that this light ray doesn't really cross that mirrored surface. It's going to boing, bounce back parallel to the ground. Follow all the same logic that we just did for the first bounce. Same thing here. Or if you like it this way, this line parallel to the ground is gonna boing, combine it with the focal point and go across through his head. Either way, boing, boing. Now, there's a couple of places where these two rays of light cross. We started both of them at the top of his head. That's one place they cross, obviously, top of his head. But the other place they also cross is right here. Guess this? And that will be the top of his head for the image. Now put his feet on the ground because you can do the whole process for his feet, just like Paul Hewitt, the basics candle, but it's still going to be on the ground. And that right there is his image. So here's object, here's image. And I'll call it a virtual image because it appears to be on the opposite side of the plane, or of the mirrored surface. Okay. If you had a true plane, you would also end up with a virtual image. Let's do a couple more convex parabolic mirrors. Let's flatten this out a bit. Okay. Now, if you flatten it out a bit, so still have a curvature to it. Okay. But when that, where would the focal point move? I don't really care about, well, maybe I'll think about center of the circle. If I flatten it out a bit, wouldn't the circle expand to be a larger circle that can fit flush to the surface right here? And wouldn't that move the center of the circle like further away? And focal point would be half of that. So let's say the focal point moves to like about here. Okay. Maybe here's the center of the circle, just barely off my page, and the focal point's like right here. Focal point. Okay. So if you either had, say, a flatter spoon, or if you got closer to that curved surface, and you could interpret it either way, it's two different interpretations, but they're going to lead to the same result. What would happen to this guy's image, right, to the reflection? Because right now I see maybe with this kind of tight curve, it's right side up, it's virtual, and it's also really tiny. I mean, it got really small. If you look at that side of the spoon, you'll see yourself, you look really tiny inside the back side of the spoon. So let's do the same procedure that we just did. We'll go one ray of light, top of his head, parallel to the ground, head straight for that surface. It's going to boing off the surface, but now align this with the focal point. And go ahead and extrapolate backwards, because that's what we did with the first one too. Okay, so as you're catching up, it did line ray of light just skirts the top of his head to this mirrored surface. It's going to bounce off in such a way that the line you could extrapolate it backwards goes straight through the focal point. Okay. Now let's pick another ray of light. Let's go from the top of his head, headed straight for that focal point. Ooh, that straight edge is just long enough. Go ahead and just extrapolate straight through the surface. Okay. Although it doesn't really cross the surface, it goes boing, it bounces off parallel to the ground again. Just like that. Okay. And see where the two lines cross? Okay, top of his head, obviously, because we made it do this, but also back here. Hey, look at this image compared to the original image. Okay. It's still a virtual image. Actually, it's not very much different result. Okay. It's a little bit bigger, and also it's closer to being equidistant from the surface, isn't it? Okay, it's a little bit closer. Huh. Hey, let's take this another step. Let's have a pretty flat type mirror. Also, for this third one, I'm going to shift further to the left. I'm going to shift the mirror to the left. You guys will see why we do this. I'm going to get really close to a flat plane. Okay. Maybe it has a little curvature to it, but not much. I'm going to put my object on the far left of the paper. So have his feet on the ground. Object. You guys good so far? Guys all right? Okay. Now, the closer you get to a flat surface, let's say it was flat, where would the focal point be? Like I see from a really tight curve, it's like here close. Then flatter, it's further away. If it was perfectly flat, how many guys think the focal point would be infinitely far away? Infinitely far away. It sure would be. Now, this one has a curvature, so I'll get it as far away as I can on the paper. I'll put it to the extreme opposite side of the paper, like right about here. Call this F for focal point. Okay. That's as much as I can spread it out. Okay, so what we're about to do is basically going to approximate a flat plane, but it's not going to be exactly a flat plane. But you guys know what a flat plane looks like. Your reflection looks a lot like you. Same height, equidistant. I think this is going to approximate that. Let's see if it actually does. And then tomorrow I'll give you guys the equations that you can use algebra to solve, and we'll also confirm what we're doing with ray diagrams. We're doing a graphical method, but there are equations for those too. And so let's go ray of light, top of his head, parallel to the ground. It's gonna boing, bounce off that surface. We're gonna align this with the focal point. This one's it's a little tricky because so far away. Some of you guys might be lucky enough to have an unbroken ruler this far into the year. So if you do, good day for you because you just whip off that line. Let's go ray of light from top of his head, aim it straight to that focal point. So this looks like that. Okay. But it doesn't really cross the surface, goes boing and bounces off back parallel to the ground again. Like that. And do you guys see where those two lines cross over here? Okay, so here's your image. And now it's still a virtual image. Okay, but hey, look at this progression, right? We started with a really tight curved mirror, and it got flatter and flatter. And now it's pretty close to a flat plane because the reflection has almost the same height as the original. It's a little shorter, but not much. And also it's pretty close to equidistant. Right? That's it. All right. Questions so far? I'm gonna get you guys set up for the next slide. So the next slide we're gonna do concave parabolic mirrors. And I'm gonna do 4 of these. So this is just you turn the spoon around. So now you're gonna look at the inside of the spoon instead of the back side of the spoon. Right? And I'm gonna do 4 examples with you guys. So I'll get this set up and then we're gonna have to pick up the story tomorrow. Right. So tomorrow we'll do some concave parabolic mirrors. Then we'll switch over and look at the equations and see, do the equations really align with what we just did using this graphical method with ray diagrams. Okay. And then we'll move on to refraction. Okay. Refraction, think of that prism, kind of like that dark side of the moon cover. You know that one? So that'll be all on tomorrow's adventure. Okay. So we're going to do 4 examples. All right, and that'll have to be a wrap on today. You guys got any questions? You guys have a good Tuesday afternoon.